To illustrate how an electrochemical cell works in general, let's talk about the Daniell cell. It's about 200 years old, it involves a zinc anode and a copper cathode. The way it works is, at the zinc anode, zinc really wants to dissolve and give up electrons. At the copper cathode, copper doesn't mind being plated out as metal, it takes up electrons when it does that. To balance the charge so that you don't end up with lots of positive charge at the zinc side and lots of negative charge at the copper side, you need some sort of salt bridge, some way to allow ions to travel through but prevent electrons from just conducting their way through and shorting the battery. One useful way to compare electrochemical cell performance is based on specific energy. How much energy can you store per gram of the battery? Now the battery is made up of all kinds of stuff, in this case copper, zinc, but also water, salt bridge material, the weight of the beakers. So the best possible energy density would be just the copper and zinc. So if we just take the copper and zinc, we know we get some voltage, we know we get 2 electrons per zinc and copper atom. We can calculate the mass of those 2 atoms, and we can calculate the energy provided by 2 electrons flowing at a certain voltage. That means we can get the best possible watt hours per gram using just straight tabular data from a freshman chemistry textbook. And it works out to be that 0.46 watt hours per gram. So an electric bicycle runs at about 500 watts. You might want it to run for about an hour to get you to the store and back. That means that you're going to need about 500 watt hours of energy storage. Now, given the energy density of the Daniell cell, that's going to require quite a lot of mass of battery. Now, this is why lithium-ion batteries are so great. Instead of 2 electrons requiring 1 copper and 1 zinc, 1 electron requires 1 lithium ion to move from the anode to the cathode. When you charge a lithium-ion battery, you pack lithium ions in between the layers of graphite. When you discharge a lithium-ion battery, that lithium comes out and migrates through the separator and ends up being reduced on the other side of the battery in something like iron phosphate. That means that the same lithium acts on both sides of the battery. That saves you quite a lot of mass. Plus, lithium itself is really, really light. So if you want to store 500 watt hours of energy, you only need so many grams of lithium. Obviously, having that upper bound to the energy density is really good, but in practical terms, no battery is ever really that good. In the Daniell cell, you have beakers and water and gel separators, and in a lithium-ion battery, you have graphite and iron phosphate and polymers and casings. So obviously, the energy density is going to be less than this maximum because of all the additional weight you're carrying. But this serves to show why some chemistries are better at storing energy than others. It's also why sodium-ion batteries haven't had the huge push. Sodium's a lot cheaper than lithium, but sodium is also a lot heavier than lithium. In practical terms, the penalty isn't as bad as it seems just from the weight of the metal itself. The real limiting factor isn't so much the weight of the metal, but rather how much of the metal you can pack into the graphite and other carrier materials. And in the case of sodium, that limitation is a little tighter than in lithium, just because it's harder to fit sodium in between the leaves of graphite than it is to fit in that very small lithium ion. So here in the Allen lab, we've been working on an all-iron chemistry with an iron anode and an iron cathode. And subtracting out all the other mass that might go into the battery, we can talk about the maximal energy density of such a cell. For every 2 electrons, we're going to need 3 atoms of iron. Iron is a fairly heavy element, and so the specific energy be worked out the same way, and it's clearly not nearly as good as the lithium ion or even the potential sodium ion. So the bad news is, in terms of watt hours per gram, iron batteries are never going to be competitive with lithium ion batteries. However, in terms of watt hours per dollar, I think iron batteries could well be competitive. Not only are they going to be cheap, but they're going to be non-flammable, non-toxic, non-reactive with water. And so I'm hopeful that they may present a friendly alternative to lithium-ion batteries for stationary energy storage, where the mass of the battery is less important. So if you're interested in hearing about that iron battery, please tune in every week. We talk about progress in our development. I have an undergraduate who's on vacation this week, but will be back soon, and he'll be making all kinds of new cells, new